Hello everybody. In this video, we're going to talk about substitutions in double integrals. And this is from section 15.8. And the keyword we're going to introduce is Jacobian matrix, which gives the factor we need to multiply when we need the chain rule or substitution rule for multiple integrals. All right, to introduce that, we take the following non-trivial example, but for demonstration purpose, it's not as complicated as it should be. But this is a rather illustrative example, and we can solve that using no substitutions, using usual integration. So in other words, we don't need any further new knowledge to solve this one because first we take dx and dy, then we know what to do. And then next we're going to use transform or substitution given by here. Using this substitution, we're going to transform the double integral problem over dx dy into du dv problems. So basically it is after transformation, we're going to have something like this and something like this and du dv. And in principle, if you have good substitution, then this is this should be easier for calculation rather than computing the first one. But the problem here when you set up is what you need to put here. What you need to put here. So those are five things, 5 spots are undetermined, which needs to be figured out when you do the substitution, and that comes from Jacobian. All right, now, so with this in mind, we first look at usual integration for the problem given here. Oh yeah, we already have this copy paste, and then we can, so for this computation, as usual, we put outside the integral, and we first work on inside the integral. So when you look at this, the antiderivative, we don't change the constant, and antiderivative of 2x is x squared, and antiderivative of y with respect to x is you look at y as constant and just multiply by x and put half of y plus 1, half of y itself, and then first I need to put upper limit to x places. So maybe I can take this 2 denominator outside of 2, so 1/2, I mean, so can. So I put denominator 2 outside, and inside I'm going to replace every x by upper limit. And now lower limit, which is and then dy. And if we compare this minus this, we get is y plus 1. And if you look at this minus this, then this term cancels this term, so it becomes negative y, so negative y dy. In other words, this is nothing but 1 inside dy, and this is 2. All right, now we know the computation. If if you, if our computation is correct, this answer gives me 2. The correct answer is 2. Now we're going to use substitution rule and try to compute the problem. And we expect number 2 as its final answer. So what is substitution? So you can look at x equals GUV, y equals HUV, right? So what it means is, so there are two functions and two variables. So it means you can look at GH as one machine. So this is GH machine, right? And when you put two numbers, U and V inside, then after you put, then you can get first X, and you can get a Y from here. So the transformation is a machine which takes two numbers in and spit out two numbers out. And you can, if you think of UV as a point here in UV plane, then after machine, it actually mapping this red dots to somewhere blue dots in XY plane. So if you to each point in the region G going through the machine, then it will form up with a bunch of new blue dots, and that gives another region R, which might have different shapes. So the idea is that suppose originally the region R is for double integral is quite irregular or something like weird complicated shape, then after substitution I want to get nicer shape for UV. Maybe we for double integral best shape to deal with is rectangular domain, right? So if you have something like triangle or circles, if you then you want to find a machine, try to transform this R into G with which gives rectangular or maybe somehow similar to rectangular domains, which is easier for our case. So to do that, another thing we want to introduce is Jacobian. So what is Jacobian? Suppose you are given a machine x equals GUV, y equals HUV. This is substitution rule, or the machine we have here, right? Then there are two functions, g and h. So we can talk about x derivative with respect to u, xv, the partial derivative of x with respect to u and v, put it in a row, and for y, you take yu, yv, put it in a row. Then this is four numbers or four expressions, gives a 2 by 2 matrix, and take the determinant, which means this. So for determinant of 2 by 2 matrix is, we mentioned before. So if you have this, then this is AD minus BC, that's the determinant. So for example, here, the determinant of this is this. So multiply this minus multiply this. All right, this is called Jacobian. And what is the use of this? So maybe we will use Jacobian to do the substitution in double integral. But one thing we want to I want to tell you earlier is, so original problem may be given dx dy order. Then what you do is, I want to do du dv after this machine transformation or substitution rule, but you have to multiply by, so if you just do dx dy equals du dv, this is not true because you did substitution. But how, so you need to adjust, or you need to multiply by some factor. What is this? This is exactly the Jacobian, or we can write this as juv, or sometimes people write this as, this is another Jacobian notation we used to write. So that means when you do the substitution integral with respect dx dy, if you want to change it du dv, then this is crucial factor you want to multiply to. All right, so with this in mind, we are going to do, for example 2, what is the Jacobian for the recommended substitution rule? So what for to do that, first thing is you want to find what is x, what is y in terms of uv. So I want to write x. So if you maybe we can just simply look at this plus this. So if you look at u equals 2x minus y, v equals 1 half y. If you add them together, then this is u plus v equals just x. In other words, x is u plus v. And from second equation, that means y, so multiply 2 both sides, right? And y equals 2v, right? So y equals 2v. So once you have x, y in terms of uv, then now it's clear what the Jacobian look like. So the Jacobian is going to be xu, xv, yu, yv, right? So xu is 1, xv is 1, yu is, because there's no u's, right? So it's basically 0, yv is 2. So 1 times 2 minus 1 times 0, which is 2. So this is Jacobian. Now we're looking at the how to use this Jacobian into substitution rule. So for double integrals, so it says, suppose you have xy plane and take the double integral of f over the region R, which is dx dy plane. Then when you do substitution, you want to change every x and y by guv and huv. This is, so x is changed by this, y is changed by this. This is obvious. This is what substitution means. Replace every xy by uv. So this is what it, and dx dy, when you replace this by du dv, you have to multiply by Jacobian. And also another key point is that after substitution, what shape of G can be expected from R. So this is another thing we want to work on for every substitution. So here there's 3 steps given for substitution rule to compute this problem. We know that this problem, if this is correct, then if the computation correct, then you should have 2 as the final answer. So we have Jacobian. We already calculated that. So the Jacobian is 2, right? Now find boundary of UV plane, or you can say it's what's the region you want to find. So we said after substitution we need following form. So there is something you want to, and du dv, right? So this is something you want. So this is something, 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 something. But the yeah, so for these 4, this defines what region of UV plane you are going to take its double integral. So we first look at the original problem. What shape of xy plane we're taking integral? So we are going to look at the xy plane. What is that? So first look at dx term. So if you look at dx term, then upper limit satisfies this. So what it means is this is y equals 2x minus 2, right? So this is one curve which describes the upper limit. So or the other hand, or in other words, the upper limit uh, the point, the ending point of the each horizontal line, which is dx, lies on this curve. And this is lower limit. For the lower limit, it's just y over 2. So that means y equals 2x. So this is for lower limit. This is for upper limit. This is for lower limit. So what it means is we have we have two. This is a curve for upper limit of x. So maybe we can say 1, 2, and suppose this is, I'm going to label this as 1, and this is curve 2. So curve 1 is here, curve 2 is lower limit, which is the same slope 2, we going through the 0, 0 origin. So this is number 2 line. And if you're talking about dx dy order, then dx describes your running horizontal line. So you're collecting all the coins on the horizontal line and then move it along dy, which means it's going up and going up. So you're moving this after collecting each line, then moving up until it goes to dy, goes out of the dy line, dy range. So what is dy range? dy range is from 0 to 4. In other words, y plus is going to be 4, y minus is 0. So there are 4 curves you're talking about. So we're, yeah. So basically, suppose this is, if I say, so if this is like, so if this is 4, and then y minus equals 0 means this just the line of x-axis, right? So if that is, so this is upper limit. So so let's say this is number 3, number 4, then upper limit for y is here, and this is for, and not this is 4. So 4 is x-axis. So in other words, maybe I should take this. In other words, our region we're looking at is the region bounded by 4 lines. 1, 2, 3, 4. 1, 2, 3, 4 lines. So it gives me this area. It's a parallelogram, so maybe I can put this with color. All right. Now so my question is, the second question is, after transformation, this parallelogram becomes new shape in UV plane. What shape do you expect? Then now we're going to just do the substitution again for equation 1, 2, 3, 4. So 1, 2, 3, 4 equations are describe those boundaries. So 1, 2, 3, 4. So we're going to see what 1 after UV. So we need to change x and y's. So we had this. So this is substitution rule we are going to use. So after using this machine, going through this machine, so if 1 is going through this machine, then it comes up with, let's say, 1 prime, right? So it is y is 2v, 2x is u plus v minus 2. So that means if I 2v cancel, so it is u equals 1. That's what it looked like. So this is one line. Number 2. Another line going through the machine after transformation, it becomes y equals 2x. Y means 2v. X means u plus v. So after calculation, it means 2v is cancelled. So u equals 0. This is 2 after transformation. Maybe I need a little bit more space. So I need to resize. Okay, so for number 3 and 4, even easier. If I put 3 into the machine, then it comes out to be this. So y equals 4. In other words, 2v equals 4, right? Then you can get v equals 2, which is 3. And again, if 4 goes into the machine, then it gives me another equation. Y equals 0 means 2v equals 0. So that means v equals 0 for this is number 4 equation. So basically we got 4 equations on UV plane, and we're going to do geometric object along this. So we need this and see what is the shape on the UV plane. Yeah, so u equals, suppose uv axis, so u equals 1, suppose this is 1, then u equals 1 means a vertical line, right? And u equals 0 for this is a vertical line, but this is v-axis. And for number 3, v equals 2, so suppose this is 2, right? Then it's a horizontal line. And v equals 0, it's u-axis. So at the end, it's a rectangular domain, which is the shape we wanted at the beginning. After, so this is 1, this is 2, this is 1. All right. Now we get, so here we go back to our original motivation. So I want this shape. Now I have du dv. Maybe I can take this, the whole thing out. Yeah, so this is what we want to do. So now we have a rectangular domain. So we have du dv. But For u, we get u is ranging from 0 to 1. For v, it's ranging from 0 to 2. Because this, and we know that dx dy becomes du dv, but this is very dangerous. When I just write du dv, you may forget the Jacobian. You have to multiply by Jacobian. And if we look back, what Jacobian is it? Jacobian is 2. So you need to multiply. When you write du dv, you have to multiply 2 as its Jacobian. And then we write whatever this is, but just do the simple replacement or substitution. So what we do is 2x. We know that x equals u plus v, right? So x 2 times u plus v. We know that 2y means minus y is 2v. So yeah, so we had y. So y from here, y equals 2v, right? So y equals 2v. Y equals 2v. And then we do calculation now. So 2v cancel. This is u. I can put this 2 outside. And du dv. So this is 0. Maybe we can just leave it there. So inside 2. So then it gives me u squared as its antiderivative. So that gives me 1 times dv, which is 2. So all right, the calculation at the end is super easy. So once you figure out this form correctly, then this is what you have. And then because of the right choice of the shape after transformation, we have 2 very super easily on the rectangle domain. But here, hard thing is how to prepare for this right form after substitution. For that, we need Jacobian here. So you need to multiply by Jacobian. So maybe I should write here Jacobian. And also, I need to figure out correct boundary after UV transfer. This is the end. We have there are some conclusions for the same example, and which was copy paste from text, so you can look at that. And so this is the illustration. Originally we have a region of parallelogram, and then we want to use rectangular domain to do that. So the solution is already solved, and there is another example, 2 more examples which I'm going to put it into next video. All right, so let's stop here.